Hello students, this is Professor Chalai, and in this video we're going to look at oxidation reduction reactions, and by the end of this video you should be able to identify the various oxidation states of atoms and compounds, and also identify the oxidized and reduced species in redox or oxidation reduction reactions. As always, you can follow along with our chapter 4 workbook. Now, so far we've been looking at chemical reactions where electrons don't really move from where they are. I know this sounds like a very strange idea, but if you think about cases, for example, with Na plus and Cl minus coming together to form NaCl aqueous, no charge is usually being transferred here. The sodium already has a positive charge, the Cl minus already has a negative charge, and when they come together to form NaCl, what we have is a situation with Na plus and a Cl minus just attracting each other by electrostatic forces. The positive charge attracts the negative charge, and negative charge attracts the positive charge. So no electron really moves. The bond is just formed because there is some electrostatic forces. And pretty much all of the other reactions that we've looked at so far in this course doesn't involve the movement of electrons. However, if we had, instead of Na plus, we have solid sodium, like without the charge, so atomic sodium, reacting with chlorine without the charge, and really chlorine without the charge doesn't exist. Chlorine without the charge would exist as Cl2, which is chlorine the gas. So to make this balance, let's just put 2 sodium atoms. In this case, when they come together to form NaCl, let's make it a solid sodium chloride, what would happen is we have a sodium atom, we have our chlorine gas. Chlorine will have to pull an electron away from sodium. And let's put our other sodium over here. Pull an electron away from sodium such that this sodium now has a plus charge, and these chlorine atoms now have a minus charge. And so in this situation, when we're starting with charge neutral stuff and then forming our ionic compounds, then we have electrons moving. So this is our electron moving this way. So in these sorts of reaction, we have electrons moving, and that is an oxidation reduction reaction. So just put simply, an oxidation reduction reaction is just simply a reaction where electrons move from one species to another. And we call it oxidation reduction reaction because the species that loses an electron and therefore becomes positively charged, or just loses an electron, is we say has become oxidized, and the species that gains an electron we say is reduced. Okay, and the way we remember that is this mnemonic oil rig, where oxidation is loss of electrons. So again, the species that lost an electron is oxidized, and reduction is gain of electrons. So the species that gained an electron is reduced. Now you might be wondering, well, how can we figure out which species gained an electron, which species lost an electron throughout the whole reaction process? Well, there's some rules for that, and we'll come back to these definitions in just a second. But the rules for that is first we need to be able to figure out what the oxidation number is, and that will tell us whether something has gained or lost an electron over the course of reaction. So an oxidation number is simply some fictitious, fictitious charge assigned to each atom in a compound. So in here, it made it easy for us because we were just dealing with one atom at a time, but sodium had a charge of 0, sodium plus had a charge of plus, so we know to go from a 0 charge to a positive charge, you must have lost an electron. In this compound, we will give chlorine charges of 0, And so it went from 0 charge to -1 charge. So to go from 0 charge to negative charge, you must gain an electron. And so that's how we figured out which one was oxidized and which one was reduced. Because we didn't actually, in this equation here, we didn't write where the electron went or where it came from. And so to figure out what those charges are, what these fictitious charges are, we have a whole bunch of rules. First rule says that if you have an atom just floating around of a free element, then the charge is 0. So in that example, we just had sodium atoms, the charge will be 0. If you have an ion that's made up of just one atom, the oxidation state is the same charge as the ion. So when we had Na+, the oxidation state, let's call it OS, was just +1. It's the same charge as the ion. All right, so those are the simple ones. The other rule, the third rule, says that if you add up all of the oxidation states for all of the atoms, you should get the total charge. This sort of makes sense. If you have a bunch of things, their fictitious charges should add up to the real total charge that they have. So if you look at a compound like, let's say, NO3-, this is nitrate ion. If you give fictitious charges to all of the nitrogen and all of the oxygen, all of the fictitious charges should add up to -1. Okay. We'll look at an example of that in a few seconds. So group 1A metals in compounds. So if you have a metal in a compound and it's group 1A, it'll always have a +1 oxidation state, and group 2A metals will always have a +2 oxidation state. So let's keep that in mind. And then finally, for nonmetals, we're going to assign oxidation state according to these numbers. And we're going to first assign fluorine, then hydrogen, then oxygen, and then so on and so forth. So if you have a fluorine, we'll just give it a state of -1. If you have hydrogen, we'll give it a state of +1, oxygen -2, and so on and so forth. And those are just simple rules to use to define oxidation states. And then if none of the rules above work, then you need to just assign oxidation states to all of the other elements that are not covered by the rules above, such that the total charge adds up to be the correct number. Seems like a lot of rules, but let's go over some examples for you. So we already did Cl2, right? Cl2. So in Cl2, we have 2 chlorine atoms, right? Chlorine, chlorine. They're halogens, they're group 7A, so typically you would assign fictitious charges of -1 to each, but the total charge over here is 0, and so we the 2 -1 charges will not add up to 0, it'll add up to -2, so in this case we'll assign fictitious charges, oxidation state of 0, to both atoms. We already talked about sodium plus. The oxidation state of sodium is +1. Let's look at Kf. In the rules in the table, we talked about how group 1A elements will have an oxidation state of +1. And also in that same table, we talked about how fluorine will always have an oxidation state of -1. In fact, potassium fluoride is an ionic compound that exists as K+ and F-. So it's really not a covalent compound. The oxidation states are already the charges of those atoms. All right, here's a tricky one. Carbon dioxide. So carbon dioxide. I'm going to draw it. Carbon dioxide. Okay, the rules say that we assign charges to nonmetals in this order. We start with fluorine, then hydrogen, and oxygen. Oxygen should have a charge of -2. Oxidation state of -2. So each of the oxygen should have an oxidation state of -2. However, the overall charge should be 0. So the oxidation state for carbon should be such that all of the oxidation states add up to 0. So if each of the oxygens are -2, you add those two up, you get -4. To balance that out, the carbon should have an oxidation state of +4. I hope that makes sense. Try SO4 2- on your own, and then let's unpause the video and then we'll go over it together. So SO4 2-, I'm just going to draw it this way. so that we can separate all of the oxygens out. And it has a total charge of 2 minus. We talked about how we always assign oxygen a charge of -2. So let's do that. -2, -2, -2. If we add all of those up, we have a total charge of -8. But the total charge is only 2 minuses. So then sulfur should have a oxidation state of +6 to balance that out. Do we see how that works? All right. Let's try this one. K2O2. This is going to be a tricky one. Okay. Potassium, we know, has an oxidation state of +1. So there are two of them, so if we add up the oxidation states for those two, we get a total of +2. The overall charge for this compound is 0. So even though oxygen typically will have an oxidation state of -2, in this case, each oxygen will only have an oxidation state of -1, such that the total oxidation states add up to 0. Again, why is that the case? Well, we use these rules in order that I've written them here. First, here, we use rule number 4 to make sure that potassium, which is in group 1A, has a +1 oxidation state. Then we apply the rules from number 5 to figure out what the oxidation state was for oxygen. We couldn't assign -2, so we move on to number 6, where we just try to add up all of the oxidation states to get a total of 0. You should be able to do these relatively easily. Let's look at CCl4. So I'm going to draw it this way so that we can see all of the different atoms. The overall charge is 0. We know from the table that if it's halogen, we are going to assign a fictitious charge of -1 to all of the halogens, the chlorides, which means that we have to assign a +4 charge to the carbon to balance the charges. All right, try all of these on your own. See if you can figure them out. If not, send me a message and I can go over them with you together. But if you follow these rules in the order that I've written them here, you should be able to assign the oxidation states to any compound. So once you can assign the oxidation states for compounds, you can do a reaction like the one I've shown you of this. There we go. Where we figure out that these guys have an oxidation state of 0. Chlorine here has an oxidation state of 0. But in NaCl, Na has an oxidation state of +1. And Cl has an oxidation state of -1. And so we realize that the oxidation states are changing, right? And so if the oxidation states are changing, we have oxidation reduction reaction. This one becomes more positive, so this was oxidized. This one becomes more negative, so it was reduced. And there we have it. Redox reactions in a nutshell. It depends on whether electrons are moving, and the way we figure out how electrons are moving is by using this fictitious charge called an oxidation state. Alright, I will see you in the next video where we go over briefly gas evolution reactions. I'll see you then. Bye.